we're going to learn about tree-based methods. For more information, you can go to Chapter 8 of the book, An Introduction to Statistical Learning. So these methods are quite different from what you have learned so far. All these methods are based at the core on a method called a decision tree, which is a way to partition and easily segment the predictor space. Let's go to this example. Let's try to predict baseball player's salary. Let's first plot our data. Each dot corresponds to a single player. The color codes the salary of that player in the log scale. And you have on the x-axis number of years a given player played in major leagues. So these are two dimensions. And we want to use those to predict what would be the log salary. You can see that clearly these people here earn less than people, for example, here. In fact, you also see that people with fewer hits would earn less than people with more hits. So if we pass this data through a decision tree, this would be a decision tree that may pop out from applying the methods on the data. This decision tree decided to split data according to two rules. First, it says, is the experience less than 5 years? If yes, then predict 5.11 log salary. If not, go to the next rule, check whether number of hits is less than 118, and if it is so, predict 6. If not, predict 6.74. As you can see, first it looks whether the person is experienced. If not, predicts very low salary. It predicts medium salary if a person is more experienced but have lower hits, and the highest salary is predicted for a person with more than 5 years of experience and more than 118 hits. Overall, you can see it is a very intuitive and straightforward way to predict based on data. As you can see in this decision tree, there were 2 decision rules and 3 terminal nodes. A regression tree is when we predict a continuous variable. When we predict a categorical variable, then we call it classification tree. We predict based on the average value of the log salaries of the players that belong to that terminal node. So this is split number 1, this is our split number 2. We call those splits, or we also can call them internal nodes. So this tree has 2 internal nodes. This tree has also 3 terminal nodes or leaves, and each leaf contains prediction. It's very intuitive. It's easy to explain to other people how to make a prediction by segmenting all the data into 3 segments or 3 regions. Okay, so graphically, people on the left were assigned to region number 1, independent on the number of hits they made in the previous year. Then people on the right were again partitioned into 2 halves, based on the number of hits. So these are our 2 split rules, and these are our 3 terminal nodes, our 3 leaves. Indeed, it did partition in a way that accords with our intuition when we eyeballed the data. As you can see, an experienced one, if we take the average of their log salaries here, we will get 5.11. If we take log salaries of baseball players in this region in our data, it will be 6. And these people in the top right got 6.74. Why did our decision tree first use number of years? Why didn't it use number of hits? What made it choose this variable to use as the first split? Why did it split at that threshold and not at another threshold, right? So there can be different things. So this is probably the most important part, like the core of the decision tree algorithm. The goal of our prediction is to minimize the square sum of residuals. Right, so we want to minimize the distance between our prediction, which falls in region J, and the true value. We want to search for the best partition. It can be done by brute force, by imagining all the different ways we can partition our data, but in fact we cannot do that because of computational complexity, so we simplify it to a recursive binary splitting. It first allocates all observations in a single node, all things together, and then it successively tries to split the predictor space in that single node. So for each predictor, it finds what would be the cut point that maximizes the drop in the sum of squared residuals by splitting the data into 2 regions. So for each predictor, it finds the ideal cut point that leads to the largest drop in the sum of squared residuals, and then it actually does the split by finding what is the best predictor with its best cut point that gives the largest drop. And now we have 2 nodes. And then it continues for each node until some stopping criteria is reached. For example, a stopping criteria can be a minimum number of observations in that node. So for example, if we do not put any stopping criteria, it will always eventually end up with 1 observation per leaf. Another splitting criteria can be some minimum drop in the sum of squared residuals. So if the split doesn't lead to a significant drop in sum of squared residuals, it stops without splitting. So let's return back to our example. We started with putting all our observations in node number 1, and we asked, what is the best split? Is it a number of years or is it number of hits? And we try different cut points for each variable. For number of years, we try different cut points for number of hits. We choose the best for years, we choose the best for hits, and then we compare between years at the best split and hits at the best split and find which one is best. We know which one. It's the number of years, our cut point 4.5. In this way we created 2 nodes. Some data will be in node number 2 and another one is in node number 3. We repeat our process by recursively splitting each node. We apply the same question to node number 2. Should we split by years or should we split by hits? And if so, which cut point? But in this case, the splitting did not occur because we reached the stopping criteria. Node 2 becomes a leaf. Same for node number 3. Should we split by years or should we split by hits? Here the answer was we should split by a number of hits, and the cutting point would be 117.5. So we repeat again for node 4 and node 5. And we reach our stopping criteria for both nodes. All end nodes are now terminal and algorithm stops. So we get as a result this decision tree, and we calculate for each leaf the prediction based on the observations that belong to each leaf.